Okay, welcome back. Well, in this lecture, we're going to take a look at carbocation stability, which is where we left off last time. Before we do that, let me just go ahead and remind you of last time Markovnikov's rule. And Markovnikov's rule from last time stated that when adding HX to an alkene, the H attaches to the carbon with fewer substituents, and the X attaches to the carbon with more substituents. Now, it turns out that a better way to state Markovnikov's rule is as follows. If I could spell it correctly, that would help. Markovnikov So the expanded version of Markovnikov's rule would state that when you're doing an electrophilic addition to an alkene, the more stable intermediate is formed. An alkene undergoes electrophilic addition reaction, the more stable intermediate. And in some cases, we'll see it may actually be a transition state. So I'm going to add that in. Is formed. And we'll explore this in a little more detail in Chapter 8 when I'll introduce some additions that don't follow Markovnikov's original rule. We call them anti-Markovnikov additions. But they actually follow this rule. The more stable intermediate is formed. So now for our carbocation intermediates, we need to know something about their stability. And the general trend in stability is that the more substituted, the more stable. So we could say, for example, or we would just say, our most stable would be tertiary, which is greater than secondary, which is greater than primary, which is greater than methyl. So that's our least stable. Most stable there. And the stability of these guys is due to what is called hyperconjugation. So one thing that's important to realize about a carbocation is that carbocations are planar. Okay, when we have that carbon, let me zoom in here. When we have that carbon with a positive charge, we have an incomplete octet. We only have 6 valence electrons, so we have a leftover p orbital. And that's the blue and red thing here. So our carbon is planar, and we have a leftover p orbital. So now that p orbital can have hyperconjugation interactions with whatever substituents are attached. So anything that's going to help stabilize that is going to, well, help stabilize it. So having more substituents will help stabilize it. There are other ways you can actually stabilize carbocations as well. And that happens to be resonance. So for example, let's say I had the following. I had C, H, H, we'll do it this way. C, H, C, H, H plus. And if I want to, I can go ahead, I'm going to push some electrons around, get my resonance structure. So now I've got H, C, H, C, H, double bond, C, H, H, with the plus over here. So initially this looks like it's a primary carbocation, but really it's resonance stabilized. The positive charge is delocalized over both ends of the molecule. So this species is as stable as a secondary carbocation. And if you had something that was, if I had like another substituent here, then it would actually be as stable as a tertiary carbocation. So we could actually go ahead and expand our stability chart here to the following. So most stable. And I'm just going to do bond line formulas here. So we have tertiary and what we call benzylic. So we have a positive charge on a carbon right next to a benzene ring. So that's our tertiary, that's benzylic. And that's going to be greater than secondary, and the one I just talked about here, which we call allylic. So this one here is secondary. And that's greater than primary, which actually I should just draw that, CH. Actually, sorry about that. Let me draw this correctly here. H3CCH plus. There's primary, which is greater in stability than our least stable carbocation is going to be the methyl carbocation. So stability of the intermediate is important, and for the reactions that we're going to be looking at, a more stable intermediate means that the product that results from that intermediate is going to be the major product, and a more stable intermediate will typically mean a faster reaction. And we'll talk about why that is in the next video. All right. Until next time, stay safe. Bye now.